Look at a star, and you expect a single story. A cloud of gas collapses. Fusion ignites. The star burns, ages, and dies. That is the contract the universe seems to sign with almost every sun, but not with all of them. There are stars that appear to break that contract. A swollen red giant, with a dead neutron star buried not around it, but inside it. A stellar corpse so dense that ordinary matter may have dissolved into a sea of strange matter. And the very first suns born after the Big Bang, so massive that instead of exploding, they may have collapsed straight into black holes. These objects do not rewrite physics, but they push our models of stellar evolution to their edge. They are the strange stars. And according to everything we think we know about how stars live and die, they should not exist. In the next 20 minutes, we will meet 3 kinds of stellar objects that challenge the standard story of star formation and death. We will stay inside the boundaries of real observations. Data from the Hubble Space Telescope, the James Webb Space Telescope, the Chandra X-ray Observatory, and ground-based surveys. But we will also be honest about the gaps. Some of these objects are confirmed. Some are candidates. Some remain theoretical predictions, waiting for a clearer signature in the noise. The goal is not to hand you comfortable answers. It is to show you why the questions are reshaping astrophysics. This is not a list of curiosities. It is a journey to the boundary where our best theories meet their limits. To understand why these objects feel so strange, we first need to remember how ordinary stars live. A star is a balancing act. Gravity pulls inward. The pressure of nuclear fusion pushes outward. While hydrogen fuses into helium in the core, the star sits on the main sequence, stable and calm. Our Sun has been there for about 4.6 billion years. The balance is called hydrostatic equilibrium. As long as fusion generates enough outward pressure, the star neither collapses nor blows apart. The mass of a star determines almost everything else: how hot it burns, how long it lives, and how it will die. A massive blue giant may spend only a few million years on the main sequence before exhausting its fuel, while a small red dwarf can burn steadily for trillions of years, longer than the current age of the universe. Eventually, the hydrogen runs out. For a star like the Sun, the core contracts and heats, the outer layers swell, and it becomes a red giant. Later, it sheds those layers as a planetary nebula and leaves behind a white dwarf, supported by electron degeneracy pressure. More massive stars fuse heavier elements in onion-like layers: carbon, neon, oxygen, silicon, until they reach iron. Iron absorbs energy rather than releasing it. The core collapses. The outer layers rebound in a supernova. What remains is either a neutron star, supported by neutron degeneracy pressure, or, if the core is massive enough, a black hole. There are hard limits along the way. A white dwarf cannot be heavier than about 1.4 solar masses. Beyond the Chandrasekhar limit, electron degeneracy pressure fails. A neutron star is supported by neutron degeneracy pressure, but general relativity adds its own ceiling, the Tolman-Oppenheimer-Volkoff limit. The exact value is uncertain, somewhere around 2 to 3 solar masses, but above it, gravity wins and a black hole forms. This ladder from main sequence star to white dwarf, neutron star, or black hole explains almost everything we see. But almost is not always. At the edges of the ladder, the rungs start to crack. In 1977, physicist Kip Thorne and astronomer Anna Zytkow asked a question. What happens if a neutron star collides with a normal companion star and sinks to its core? Their calculations suggested something extraordinary. The neutron star could settle inside a red supergiant, orbiting the common center of mass, swallowing gas, and altering the star from within. We now call this a Thorne-Zytkow object, or Tease for short. It would look, from the outside, like an unusually cool and luminous red supergiant, but its chemistry would betray it. Nuclear reactions around the neutron star core should create unusual abundances of lithium, molybdenum, rubidium, and other elements. The star would rotate more slowly than a typical red supergiant of the same temperature, and it would shine in a particular way. The scenario probably begins with a close binary system. The more massive star evolves first, explodes as a supernova, and leaves behind a neutron star. Over time, gravitational interactions, tides, and a common envelope of shared gas can drag the neutron star inward. If it spirals all the way to the center, it lands in the core of the companion, which by then has swollen into a red supergiant. The TGO could live for hundreds of thousands of years before friction, mass transfer, or a final merger disrupts the arrangement. For decades, TGOs remained a prediction without a confirmed example. Then, in 2014, a team led by astronomer Emily Levesque reported a candidate. The star, known as HV 2112, sits in the Small Magellanic Cloud, a dwarf galaxy orbiting our Milky Way. Its spectrum showed chemical oddities that matched some of the predicted TGO signatures. The discovery made headlines: a star with a neutron star for a heart. Levesque and her team used the Magellan telescopes in Chile to collect the star's spectrum, then compared it to detailed models of red supergiant atmospheres. The match was intriguing. HV 2112 was cooler and more luminous than expected, with chemical fingerprints that looked like the aftermath of nuclear burning around a neutron star furnace. But science does not end with a single candidate. Later studies, including work by Christopher Tout and collaborators, re-examined HV 2112 and suggested it is more likely a peculiar red supergiant with unusual internal mixing, not a neutron star embedded in a star. Current evidence points away from HV 2112 being a true TGO. That does not mean Thorne-Zytkow objects do not exist. Binary evolution is messy. Neutron stars and black holes merge with companions in ways we are still learning to model. Searches continue with larger surveys and better spectroscopy. The absence of a confirmed TGO tells us something important. Either they are rare, or their signatures are subtler than we assumed, or both. If one is ever confirmed, it would be a laboratory for matter under conditions we cannot replicate on Earth, and a direct test of how stars exchange material in the final stages of their lives. The next category takes us deeper, into the interior of a neutron star. A neutron star is already extreme. More mass than the Sun, packed into a sphere only about 20 kilometers across. A sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. But what happens if you squeeze it even harder? One theory suggests that neutrons themselves break down. The quarks inside neutrons, Up quarks and down quarks would no longer be confined inside neutrons and protons. They would form a sea of deconfined quark matter. If strange quarks are also present, the object is sometimes called a strange star. The idea connects to one of the deepest questions in physics. Could strange quark matter be more stable than ordinary atomic nuclei? If so, a strange star would be matter in a state we have never produced in a laboratory. The idea traces back to a 1984 paper by physicist Edward Witten, who pointed out that if strange quark matter is truly the lowest energy state of hadronic matter, then ordinary nuclei might be only metastable. A strangelet, a small lump of strange quark matter, could theoretically convert anything it touched into more strange matter. Most physicists think this scenario is unlikely, because atomic nuclei have remained stable for billions of years. Still, the possibility keeps the strange star hypothesis alive as a testable prediction. Some astrophysicists have pointed to compact objects that behave oddly and asked whether they might be quark stars instead of neutron stars. One candidate is RX J185653754, an isolated neutron star whose inferred size, in some older analyses, seemed smaller than expected. Another is 3C58, the pulsar remnant of a supernova observed in the year 1181. It appears cooler than standard neutron star cooling models predict, which a quark star interior might explain. There are also rapidly spinning objects, such as XTE J1739285, whose reported rotation rate raised eyebrows. Another way to test the idea is to measure the size and mass of a neutron star with extraordinary precision. NICER, an X-ray telescope mounted on the International Space Station, does exactly that by tracking hot spots on spinning neutron stars. If a compact object were significantly smaller than the stiffest neutron star models allow, a quark star explanation would become much harder to ignore. So far, NICER measurements have favored more conventional equations of state, but the data are still accumulating. However, each of these cases has alternative explanations. Distance measurements to RX J1856.53754 were revised, making its radius look more normal. Cooling anomalies can be explained by different crust models, and the extreme spin measurements have not held up under scrutiny. Current evidence points to these objects being unusual neutron stars, not confirmed quark stars. Still, we cannot rule out the existence of quark stars. Future observations from NICER and proposed observatories may one day find a compact object that simply cannot be a neutron star. If that happens, it will be the discovery of a new state of matter. Let us travel further back, to the first generation of stars. Astronomers call them population 3 stars. They formed when the universe was only a few 100 million years old, from gas made almost entirely of hydrogen and helium, with virtually no heavier elements. Without carbon, oxygen, and iron to cool the gas efficiently, the clouds may have grown far more massive than stars forming today. One theory suggests that the very first stars could have reached hundreds, perhaps over 1,000, solar masses. At that scale, a star is less a stable sphere and more a barely contained thermonuclear bomb. Its radiation pressure would be enormous. Its core would forge elements far beyond iron, and its death would be unlike anything in the local universe. Because they lacked heavy elements, Population 3 stars would have been extremely hot and blue, emitting intense ultraviolet light. That light is one of the main suspects for reionizing the neutral hydrogen that filled the early universe, turning the cosmic fog back into a transparent plasma. Their deaths would also have produced the first heavy elements, which were then incorporated into the next generation of stars, known as Population 2. Some of the oldest Population 2 stars we see today in the Milky Way's halo carry chemical traces that may be the diluted fingerprints of Population 3 ancestors. For the most massive Population 3 stars, one theory suggests direct collapse. Instead of a supernova that expels much of the star, the entire object collapses into a black hole of tens of thousands of solar masses. These direct collapse black holes could have been the seeds of the supermassive black holes we see today, billion solar mass monsters already shining when the universe was less than 1 billion years old. Astronomers are hunting these early objects with several tools. The James Webb Space Telescope's infrared eyes can see the light of galaxies stretched by cosmic expansion. ALMA, the Atacama Large Millimeter, Submillimeter Array, can detect the cold gas and dust surrounding young galaxies. Chandra sees the X-rays blazing from hot gas, spiraling into a black hole. When all three point at the same patch of sky, they can separate starlight from black hole accretion, a crucial distinction when the objects are so far away. We have not yet taken a clear photograph of an individual Population 3 star. The James Webb Space Telescope is now hunting them by searching for the telltale light of extremely distant galaxies. Some early JWST observations revealed galaxies at redshifts greater than 10 that are brighter and more massive than many models predicted. One interpretation is that they host unusually large populations of massive, hot stars, perhaps close cousins of Population 3 stars, or accreting black holes. There is also WHL 0137 LS, nicknamed Arundel, the most distant individual star known through gravitational lensing, detected by Hubble and studied by Webb. At a redshift of roughly 6.2, Arundel is not quite a Population 3 star, but it shows that the early universe could magnify single stars across cosmic time. Detecting Arundel required a perfect alignment. A massive foreground cluster of galaxies warped space itself, magnifying the light of a star that would otherwise be far too faint to see. Webb follow-up observations are measuring its temperature, mass, and chemical makeup, telling us what kind of star could shine so brightly at such an early epoch. And the galaxy UHZ-1, revealed by JWST and Chandra X-ray observations, hosts a black hole at a redshift around 10, so early that it challenges simple models of black hole growth. Astronomers are debating whether it formed from direct collapse, from rapid accretion, onto a smaller seed, or something else entirely. The story of the first stars is still being written, observation by observation. So why do these strange stars matter? Each one sits at a boundary where our best theories meet their limits. Thorne-Zytkow Objects test our understanding of binary star evolution and the way matter is exchanged when one star becomes a neutron star. Quark stars probe the equation of state of ultra-dense matter, a regime where nuclear physics and quantum chromodynamics, the theory of the strong force, become inseparable. Population 3 stars and direct collapse black holes connect star formation to the reionization of the universe and the origin of the supermassive black holes that now anchor most large galaxies. These objects also point toward the future of multi-messenger astronomy. Gravitational wave observatories like LIGO, Virgo, and Kagra are already catching collisions between neutron stars. The way a neutron star merger rings after impact carries information about how squishy or stiff neutron star matter is. If quark matter exists inside some neutron stars, those merger signals might contain subtle echoes that current detectors can barely resolve. Future facilities, and perhaps third-generation gravitational wave detectors, could turn those whispers into data. What unites them is uncertainty. We do not yet know whether Thorne-Zytkow objects are common, rare, or non-existent. We do not yet know whether quark matter forms stable stars. We do not yet know exactly how massive the first stars were, or how the earliest black holes grew so large so quickly. Each answer will ripple outward. A confirmed Thorne-Zytkow object would force stellar evolution models to account for mergers that happen deep inside a living star. A confirmed quark star would mean we have found a macroscopic chunk of matter in a form never seen on Earth. And a clear detection of population 3 stars would rewrite our timeline of cosmic chemical enrichment and the first galaxies. But in astrophysics, uncertainty is not failure. It is a map of the next frontier. Every candidate object that turns out to be something more ordinary teaches us how to sharpen our models. Every confirmed anomaly rewrites a chapter of the textbook. The strange stars are not contradictions of science. They are invitations to look closer, to build better telescopes, and to keep asking what else might be hiding in the dark. The night sky is not a finished museum. It is a workshop, still under construction. The stars that seem to challenge our models today may become the standard models of tomorrow. The next time you look up, remember that some of the most important stars may be the ones we have not yet learned to recognize. If you want to keep exploring the edges of the known, our next episode will dive into the hidden ocean worlds of the outer solar system. Moons where liquid water may slosh beneath shells of ice, and where the question of life is far from settled. Subscribe and hit the notification bell if you want to be there when it goes live. Thank you for watching, and we will see you next time.